Hello, this is Richard Collins, your instructor in ATM 101 Weather and Climate of Alaska here at the University of Alaska Fairbanks. Welcome to Unit 14, Climate and Climate Change. In this first slide we see a Time magazine cover from 2007 with the question, who owns the Arctic? This cover focuses on the geopolitical side rather than the environmental side of Arctic climate change. Rather than showing a polar bear isolated on the ice floe, the cover shows a cluster of flags of the Arctic nations: Canada, Denmark, Norway, Russia, and the United States. The change in Arctic sea ice will change access to the Arctic and its natural resources. The geopolitical discussion quickly becomes a discussion, or argument, about which countries own the natural resources of the Arctic. The overarching question for this unit is, what are the factors that shape climate and climate change? The four specific questions are, how do we describe climate? What are the primary controls on climate? How do these controls vary? And what does climate change look like? I hope you can apply the meteorological knowledge and understanding of meteorological processes that you have acquired over the whole semester to your study of climate and climate change in our final unit.
Climate is the average weather condition or the prevailing pattern of weather at a given location. There's also a much more general idea of climate behind that. There's an ecological idea of climate, the kind of plants we have, the kind of agriculture it supports, the environment, the full environment that we live in associated with climate. On the right is climate data for Fairbanks, and it shows the monthly temperatures going from minus 10 degrees Fahrenheit to 60 degrees Fahrenheit through the year. And below it, the precipitation, showing precipitation in January, all of it snow, unless we get very strange conditions with freezing rain, but then a peak in precipitation in August, the rainy season in Fairbanks. And below it, a typical picture from the Fairbanks area showing the spruce trees, a landscape called taiga, as it's called in Siberia, of spruce trees and lakes. And the reason that even though we get a very small amount of rain through the year, 11 inches, so climatologically we're a desert, our small annual average temperature, which is below freezing Celsius, means that there's not much evaporation in Fairbanks. So any water we do get tends to stay in the ground and support the boreal forest, the forest of spruce trees and birch trees that spans the globe at high latitudes across Eurasia and North America. We're going to talk about controls on climate and highlight how latitude and solar intensity, the distribution of land and water, ocean currents, prevailing winds, the position of high and or low pressure systems, mountains, elevation, and albedo control climate. We're also going to limit our discussion of climate primarily to temperature and precipitation. And so we're going to look at global patterns of temperature and precipitation in the context of these controls. The map shows the distribution of temperature for the month of January. These are monthly average temperatures averaged over many years. We see that it's January because we have numbers like minus 35 Celsius over North America, minus 50 Celsius over northern Siberia, temperatures of about 10 degrees Celsius off the tip of South America. I've identified 10 regions where different controls are at work to highlight how controls on temperature work in the climate system. So I'm going to go through these one by one and explain the features and the physical situation that gives us the features that we see. I'm going to start actually with B, because this shows temperature control by sunlight and latitude. In B, in the Southern Ocean, we see that the isotherms have horizontal lines. If I was to travel southward, I would just see that the temperature was getting steadily colder as I headed toward the South Pole from the equator here in the South Pacific. The lines are horizontal, meaning that the temperature just follows latitude. As I go from one latitude to the next, it gets steadily colder at all points on that latitude in this region. And the reason for this is that as latitude goes from 20 south to 50 south, the sun is getting lower in the sky, therefore the Sunbeams on the ground are spreading over a wider area as I head away from the equator, and the sunlight is more dilute and therefore is heating the ground less. Everything we saw in the early chapters of our textbook and studied in terms of solar elevation and heating. And so this is what we would expect on a planet with no geography. We would expect that the isotherms would just be lines following latitude around the world. If we now introduce geography, land-sea contrast for example, and we go up to A in Alaska, we see that it's winter time. The continent will cool much more than the ocean due to both the specific heat of water relative to ground and also due to the emissivity of the ground relative to the ocean. And so we have, if I travel east-west across the Gulf of Alaska, I get much colder temperatures inland over the land than I get over the ocean. And so my contours, as I travel from the Pacific towards the North America, I get that my contours move downward because cold temperatures are pushing downward from the polar region in the interior of the continent, or if you want to think of it, warm temperatures are pushing upward over the ocean toward the pole. And that's why I get the change in contours there that I get. If I go down to C, I have an example here in the Andes of how elevation leads to cool temperatures. You'll see that the 15 degrees Celsius contour at 40 degrees south turns and makes its way up to the equator following the Andes. And the reason for this, as we've seen earlier in the textbook and in the class, is that at high elevation you have less atmosphere above your head, and therefore you have less greenhouse effect keeping the ground warm and the air above the ground warm. It's easier to radiate heat to space because there's less atmosphere above you, and there's less atmosphere above you to re-radiate heat back to Earth. So there's less of a greenhouse effect and we get cooler temperatures. D, off the coast of Peru and Chile, is an example of where a cold ocean current is pushing water equatorward and therefore giving us cold temperatures off the coast. If you go back and look at the distribution of ocean currents, there is the Peru current off the coast of Chile and Peru that is carrying water towards the equator along the coast of South America. In E, we have another example of land-water distribution, but now in the summer hemisphere where the land is warmer than the ocean. It's not as extreme a situation as we find in the winter hemisphere, where the contours are very sharply kinked over land. Here we see an easier change, but there still is a change where the water is colder than the land, and therefore if I travel east-west out from South America over the South Atlantic, I see that my isotherms move equatorward because I move from warm air to steadily colder air. If I go up to F in Western Europe, this is the rock star example of warm ocean currents. This is an example of the Gulf Stream bringing heat from the Gulf of Mexico across the North Atlantic to northwestern Europe. And it's why the temperature in northwestern Europe is at about 10 degrees Celsius when at the same latitude in Siberia or in North America we see temperatures well below freezing. And it's the reason for the generally temperate climate in Western Europe. The contours are all pushed poleward in the Western European part of the world. If I go down to G, I see the effects, like I did with the Peru current, of the South Atlantic current, which travels northward along the coast of West Africa, Southwest Africa, Namibia in particular, and brings colder water equatorward. If I go to H, I see the effects of low solar elevation. There's very low solar elevation. We're near the Arctic Circle. We get a radiation high pressure system over Siberia. It's not one of the permanent highs and lows. It appears in the winter. It's due to cooling of the ground, descent of air, dense air in that cooling, which creates a anticyclone, which gives us clear skies, which allows for more cooling in the descending air, and so we get this very cold, stable air over central Siberia. And it's due to the size of the Eurasian landmass and the isolation of the Eurasian landmass that we don't get such an extreme steady behavior over North America. We do get an attempt in the to get radiation highs over Canada, but they're not as extreme as the ones over Siberia. If I go to I, this is an example in the winter hemisphere again of contours that are relatively horizontal, and again showing just the latitudinal effect that as we change latitude we see temperature changes. As we move away from the sun in latitude, we steadily get colder. It's also important to point out that the contrast in the northern hemisphere in winter in the northern hemisphere is more pronounced than in the southern hemisphere, that the range of solar angles in the winter hemisphere go all the way down to 0. And so the range of temperatures in the winter hemisphere is always going to be more dramatic than the range of temperatures in the southern hemisphere, because the range of solar angles is not as extreme in the summer hemisphere. Finally, in J, we see temperatures of 30 degrees Celsius, the warmest temperatures on the map in Central Australia, which is a desert region. And this reflects the effects of cloud cover, that we have these clear sky regions at about 30 degrees south and 30 degrees north embedded in the general circulation where we have clear skies. The great desert regions of the earth are not at the equator where you think the sun is more overhead, but they're about 30 degrees north and south. And this is the example of the great desert in Australia where we have clear skies and very high temperatures. I now turn to the average temperatures in July, and I'm going to leave it to you as students to go through and work out for yourselves which is which. This is July. How can I tell it's July? Well, because the average temperature in Fairbanks is about 10 degrees Celsius. The temperatures in Europe are about 20 degrees Celsius, and now the temperatures off South America are about 0 degrees Celsius. Going through this very quickly, A shows land-sea contrast where the land is warmer than the sea. B shows the cold California current off the coast of California. C shows latitude change. E shows the cold Peru current. D shows high elevation in the Andes. What's new in this that we didn't consider in January, in F over Greenland, the very cold temperatures in Greenland relative to similar latitudes in the northern hemisphere, even though we have 24-hour sunshine, is the albedo, the fact that Greenland is covered in ice and therefore doesn't warm up hugely in the summer. It reflects sunlight quite effectively compared to other areas in the polar regions in the Arctic, and so it remains very cold. So F is an example of high albedo. G is the great deserts over North Africa, the Sahara Desert, similar as we saw over Australia in its summer hemisphere, and we see very high temperatures, 35 degrees Celsius. You notice we also see 30 degree Celsius temperatures in the American Southwest for similar regions, desert regions there also. H shows high elevation, the Tibetan Plateau, 20 degrees Celsius embedded in 25 degrees Celsius around it. And I, off the coast of Russia, north of the Korean Peninsula and over Japan, we see that we have land-sea contrast where we have warmer temperatures over land than the ocean, and we have a kink in the contours as we head out to sea. If we talk now about precipitation, how we understand the global pattern of precipitation is embedded in our 3-cell model of the atmospheric circulation. We've seen where we have the Hadley cell at the equator, rising air with the intertropical convergence zone, and we just get deep convection and rain and thunderstorms all year round. Where at the edge of the intertropical convergence zone we get wet summers and dry winters. And then as we move out to where the air descends in the Hadley cell, we get clear skies in the descending air, and that's where the deserts are, and all seasons are dry. As we move out to the Ferrel cell, we tend to get dry summers and wet winters, and then at the polar front we tend to get, where the polar cell and the Ferrel cell meet, we get all seasons are wet. The typical weather of the Aleutians, where there's just endless rain along the polar front. And then poleward of the polar front, we tend to get all seasons are dry. The other thing that's in the mix here, as well as the pattern of rising and falling air giving us precipitation, or lack of precipitation when it's falling, is the fact that as the air gets cooler, the capacity to hold water in the air goes down. The absolute humidity of the air decreases as we go from the equator generally toward the poles as temperatures cool, and therefore we expect there to be less water vapor in the air. Relative humidities might be high, but absolute humidities are not high as we go towards the pole, and therefore we tend to have all seasons dry in the polar regions. We have a map of global precipitation, the total precipitation for the year around the globe, and the color shading is in millimeters, getting greener with more rain. 200 millimeters is approximately 8 inches. There's 25 millimeters to an inch, if you want to think of this in inches. And again, I've identified regions around the world where there are key controls at work in the precipitation. In A, we see along the coast of Alaska, the southern coast, we have a distinct and pronounced precipitation region, and this is of course where winds come into Alaska and travel over the Chugach and Alaska ranges in the south central part of the state. The air rises, the air cools. As it cools, its capacity to hold moisture decreases. We get condensation, formation of clouds and rain on the south side of those mountains, and then as the air travels inland, it has lost its moisture and generally it's much drier, and so the interior of Alaska is a rain shadow of the Alaska range. We have the same effect in B for the coastal mountains of the Pacific Northwest. Winds coming from the west, westerly winds, reach the coast full of moisture, rise over the mountains, cool, and deposit their moisture as rain and give rise to the great rainforests that we have in the Pacific Northwest. In contrast, in C, we see dry regions in California on the same coast, and here the reason is, of course, the cold coastal waters. So we have water coming in off the Pacific, 100% relative humidity, warmish ocean water coming in. It reaches the coastal waters and it's chilled, and therefore it loses its capacity to hold water, and we get fog off the coast of California. Having lost that moisture, the wind continues inland and is now much drier, and so there's less moisture left to form rain over the land, and we get the desert regions again of the American Southwest. When we go to D in the southeastern United States, what we're actually seeing is the influence of the Bermuda or Azores anticyclone or high pressure system. In a high pressure system, we're getting clockwise winds in the northern hemisphere, and so the pattern of the winds is that the anticyclone sits off the coast in the Atlantic and drives winds from the Gulf of Mexico in over the southern United States and carries moisture into the southeastern United States, the Gulf states, and brings a huge amount of moisture from the warm waters of the Gulf. Going to E, we see that we're in the intertropical convergence zone over the Amazon basin, and so we have essentially latitude control of precipitation, the intense convection under the high elevation sun near the equator. In F, we have a similar situation as C. The Peru current causes fog off the coast, and air continuing on in overland has very little moisture, and we get dry desert regions in northern Chile. In G, the moisture that we see in Western Europe is due to the prevailing winds from the west over the warm waters of the Gulf Stream, carrying moisture in over Britain and Ireland, which are famously wet and rainy. In H, we see the counterpoint to E in the descending cell of the Hadley circulation cell. We see descending air, clear skies, and the desert regions of North Africa. In I, we see the African component of the intertropical convergence zone and the great rainforests that we see in Central Africa. It's the counterpoint to the Amazonian situation in South America. J is again a desert example with a cold coastal current, just as in F and C. K is an example of moving highs and lows, the monsoon circulation, where we get low pressure in summer drawing air off the Indian Ocean across South Asia and arriving as the geography rises up against the Himalayas and getting great rains associated with the monsoons. So the monsoon rains are at K in South Asia, and that's associated with the movement of high and low pressure systems, just as in D is controlling the moisture in southeastern United States. L is for Indonesia. The high rains are again the intertropical convergence zone, just as I and E are. And M is a control by latitude also. It's the Australian deserts. It's the counterpoint in the southern hemisphere of the deserts in North Africa. We get descending air in the falling side of the Hadley cell, clear skies, and not much moisture. The seasonal precipitation patterns over the United States are plotted here. In the upper left is the July climatology, showing a general pattern of lots of rain in the American southeast and very little rain in the American southwest. In winter, there's still significant rain in the southeast, but we are seeing rain in the southwest. And the west coast pattern is due to the movement of the Pacific high pressure system, which blocks rain in the summer. The eastern side of the high pressure system is bringing cold, dry air in a clockwise rotation down over California, and we get little rain. In winter, the Pacific high moves south and allows storms to come in off the coast and bring rain into the west coast. In summer, in the southeast, the Bermuda high is bringing warm, moist air over the Gulf states. In winter, the Bermuda high moves south, allowing storms ashore on the west coast, traveling across the United States and bringing precipitation. So this pattern highlights the movement of high and low pressure systems in the climate in terms of precipitation and seasonal changes in precipitation. I just want to highlight where we've been in the spring of 2012. These maps represent temperature anomalies. The blue are cold and the red are warm, and it gives you a sort of instinctive view of how the temperatures have been for a month around the world relative to the average temperatures for the region for the period 1971 through 2000. And we see in January that the temperatures over Alaska were unusually cold, while the temperatures over the main United States were warm. In February, temperatures over North America were generally warmer than climatology. And then back in March, we find again that temperatures in Alaska are colder than we would expect. So this gives you a seasonal perspective to the kind of weather you've been looking at in Alaska, where January and March were colder than we expect and February was warmer. It also speaks to just the amount of variability in the climate system. What does it mean to be in a year where January was unusually cold, February was unusually warm, March was unusually cold? What does that mean in the average climate, and how do we make sense of it if we believe that we're in a cycle of general global warming? The variability in the climate system makes it very hard to make short-term conclusions about what the climate is doing, and that's why we average climate over 30-year periods. There are some people even arguing that 30 years is not enough, that there's variability in the climate over 100-year periods. You really need to have 100-year records to tell what's happening. As we talk about temperature change in Alaska, the table here highlights temperature change in stations in Alaska in different seasons, and then the annual average of change in degrees Fahrenheit, and it's color coded to show the intensity of warming and cooling. There are places in Alaska where we see cooling over this period, in Fairbanks in autumn and in Kodiak in autumn. However, in general, we see warming across the state. This is over the 50-year period at the end of the 20th century, from about 1949 to 2005. And we see the most significant warming is occurring in the winter, most pronounced warming, followed by spring, then summer, and finally autumn. And you can see the annual numbers. Talkeetna stands out as having a lot of warming, and that may also reflect the fact that Talkeetna is nestled in at the base of the Alaska Range, and there may be mountain weather effects there as well. We generally see, though, that the interior of Alaska has warmed quite significantly over this period. And on the west coast, there's significant warming also in Bethel and King Salmon. So closing thoughts and summary for this unit. The Earth is a planet of many climates, and how we define climate, we are defining it in the terms of the class. We're just talking about temperature and precipitation as the key parts of climate, but clearly the type of biology supported is also an issue of climate, the type of agriculture that's supported. It's important to remember that places can have the same annual average temperature in very different climates. So for example, the San Francisco and Richmond, Virginia have the same annual temperature of 57 degrees Fahrenheit, but incredibly different climates. If you go back to the United States precipitation maps and you look at Virginia on the East Coast and California on the West Coast, you see just how different the rainfall patterns are. And if you've been to both places, you recognize that the summer and winters are very different, even though the annual average temperature is the same. Climate is controlled by a variety of factors. Climate is more, as I say, just an average temperature. The pattern of the general circulation contributes to the large climate zones, the rainy weather we get in the Aleutians, the great desert regions we get around the world. The pattern and movement of highs and lows contributes to the climate, and we see that in the seasonal changes in climate, in great climate systems like the monsoons. This is a critical question in understanding climate change. If the pattern of highs and lows were to shift due to climate change, say in a greenhouse warming scenario, that would be a much more dramatic effect than just the energy balance effect of increased greenhouse gases in the atmosphere. That would drive questions of precipitation, temperature, and cloud cover much more dramatically, those regional changes associated with the highs and lows, than if you want the average bathtub effect of the average atmosphere changing its temperature due to increased carbon dioxide. So if the changes in carbon dioxide were to induce changes in the high and low pressure system patterns, that would be a major consequence of climate change. Year-to-year variability makes understanding climate and climate change hard. And finally, climate varies at a variety of temporal and spatial scales. If we look at the pattern of change across the state of Alaska, we see different types of change in different regions of the state. It's not that everywhere is warming uniformly. And we also see, again, changes on different time scales, and this relates back to El Niños, Pacific decadal oscillations, and all those other parts of the system that vary at 10 or 20 year scales.